Hi, I want to talk about wave vocabulary and how to read harmonic wave functions. Now, in general, a wave is a way of transmitting energy from one place to another where whatever form that energy is taking, it maintains its shape by having a phase that evolves so that if I had a function of space and time, my function depends on space and time in the form of my position minus the velocity of my energy times time remains constant. Now, it sounds a little weird to say it that way. One way to think about that is, say I were to just draw some sort of spike and watch that move across the board. That's an example of a wave pulse. As long as it maintains that exact same shape as it moves, then all points are moving so that the location at any given time minus the speed of that pulse times the amount of time that's elapsed is going to remain constant. Usually though, when we're talking about waves, we're going to be talking about what we call harmonic waves. And a harmonic wave is just a wave that has a period or a frequency f or a natural frequency omega or angular frequency omega in radians per second. So that means we'd be dealing with something that would have a sinusoidal shape. So if we were to take a look at that shape, there would be some equilibrium position. For the case of a wave on a string, where the string would just be flat. Or for a wave on the water, where the water would just be flat and still. Or for an electrical or magnetic wave, where there would just be no electric or magnetic field. The distance from that equilibrium point to the maximum point, either above or below, is what we call the amplitude of our wave. And it's customary, particularly when we talk about things like water waves or waves on a string, to refer to the maximum, what we would consider positive, which usually means upward displacement, to be a crest, and the minimum sort of displacement, the maximum negative displacement, to be called the trough of a wave. Now, the other feature that has to deal with space is what happens if we take a look from one feature of the wave to the next feature of that wave. For a harmonic wave, every crest is going to be the exact same distance away from every other crest, moving forward or backward along the wave. Every trough is going to be the same distance away from every other trough, and it's the same distance as the distance between the crest. Every point on the wave where at equilibrium and rising is going to be the same distance away from where we're at equilibrium and rising. All points on this wave repeat at a distance that we call the wavelength, and the symbol we use is the lowercase Greek letter lambda. The lowercase Greek letter L for length, the length of a wave. Now there's one more terminology piece that folks sometimes use when describing waves, and it's easy to confuse what they're saying when they say this with the wavelength. Now, that description is what's called a peak-to-peak measurement. And you might think, well, peak-to-peak, that's crest to crest. That would be a measurement of the wavelength. What people mean when they say peak-to-peak is from the positive peak, the upper peak, to the lower peak. The difference between crests and troughs. And for any harmonic wave, peak-to-peak differences are exactly twice the amplitude. So in electronics, a place where peak-to-peak comes up a lot is if you're taking a look at an electrical signal on an oscilloscope, sometimes it's easier to measure where the top of the signal is, where the bottom of the signal is, and we can just say, oh, well, the amplitude's going to be half of that easy to measure distance, that peak-to-peak difference. So peak-to-peak, twice the amplitude, crest to crest, trough to trough, those are what we call lengths of our wave, or wavelengths. Now for any harmonic wave, it could be expressed in terms of a sine or a cosine function. I'm going to write things out in terms of a sine. And honestly, the only difference between a sine and a cosine is a little bit of extra angle added into the oscillating term in the argument of our sine or cosine function. So in general, a harmonic wave would have a y-coordinate as a function of space and time, x and t, that would be equal to our maximum displacement, our amplitude, times the sine of 2 pi divided by our wavelength times our position minus our velocity times time. This dependence between x and t is what makes this a wave, and both of those have units of distance. So if we divide by the wavelength, each wavelength would add 2 pi radians of phase along our wave. So that's why we end up choosing that piece. And as I said, we could add in some arbitrary angle to figure out exactly where our wave is starting compared to where a sine wave, or a cosine if that's what you're using, starts. Well, 2 pi over our wavelength has a name for it in another symbol we use. 2 pi over the wavelength lambda is defined as the wave number, or more appropriately, angular wave number. Even though angular wave number is more appropriate, most folks will just call that value k the wave number. And what it's telling you is how many radians of phase that wave would evolve per meter of distance traveled along our wave function. Now, in order for our wave to maintain its shape, I said that this had to be a constant. Our position minus our velocity times time had to stay fixed. So let's say we travel a distance of 1 wavelength. Well, for the wave to travel a distance of 1 wavelength, all of the wave carriers need to evolve through exactly 1 period in their phase. So the wavelength minus the speed of our wave times the period would have to equal 0. So for a wave then, the speed of a wave is the wavelength divided by the period, and since 1 over the period is my frequency f, the speed of a wave is also the wavelength times my frequency f. Well, we also, I said, could describe it in terms of our angular frequency, omega. And omega is 2 pi times f. Our angular wave number is 2 pi divided by lambda. So the final way that we could express the wave speed would be equal to our angular frequency omega divided by our angular wave number k. So a more compact and common way that you'll see the wave equation written will be our wave as a function of space and time is equal to our amplitude times the sine or cosine of our angular wave number k times our position minus our angular frequency omega times time. Thanks for watching.